Imagine a single, inefficient line of Python code. It takes exactly 1 extra millisecond to execute. On its own, a delay of 1,000th of a second is practically invisible. But put that code inside a for loop executing 1 million times, and the math changes. The processor stalls for 16 minutes. This delay cascades. Database queries queue, API request timeout, secondary systems freeze until memory runs out. Because of its repeating architecture, a simple loop inevitably turns microscopic inefficiencies into macroscopic system crashes. Traditional static analyzers, or linters, exist to catch bad code before it runs. Standard linters identify almost everything. They flag a missing comma and a catastrophic memory leak with the exact same visual weight. When thousands of identical warnings scroll down the terminal before a release, you are paralyzed without hard data. Without a quantifiable way to measure the performance cost of a warning, code optimization is reduced to a dangerous guessing game. The loop anti-pattern linter was engineered specifically to calculate the real-world cost of bad logic. It operates by converting your code into an abstract syntax tree, or AST. Think of this as a mathematical map that breaks down the structural relationship of your script, piece by piece. The linter uses a NodeVisitor subclass to traverse this map. It navigates down the branches, inspecting loops and variables strictly by looking at their architecture. Because it reads the structure instead of running the code, the scanning process requires zero runtime overhead. It calculates the damage mathematically. By evaluating the static tree, the linter acts as a preemptive radar, catching architectural failures before they enter a live environment. To find the most dangerous bottlenecks, the linter relies on 5 distinct AST-based loop detectors. This bar chart shows the projected slowdown for different types of errors. The lowest bar represents the Lennon loop anti-pattern. If you recalculate the length of a list inside a loop instead of caching it beforehand, you incur a mild penalty, roughly a 10% slowdown. Use a .append method inside a loop instead of a standard list comprehension, and that penalty jumps up to 30%. Then there is the nested loop same iterable pattern. Looping over the exact same dataset twice triggers a massive 50% slowdown. These curves illustrate Big O heuristics, a mathematical way of measuring how execution time scales with data size. By applying these heuristics, the tool turns abstract code habits into hard quantitative estimates. This table demonstrates how the tool processes those metrics. It appends an estimated slowdown PCT column to its output, and then literally resorts the findings, so the most severe errors sit directly at the top. That automatic sorting mathematically transforms an overwhelming list of errors into a precise, prioritized hit list for the developer. Knowing what to fix first is only half the workflow. The linter's //explain flag handles the actual repair. By routing the flagged code through OpenRouter, defaulting to Claude, the linter generates natural language context for the moth. It reads your specific loop and provides actionable instructions, like suggesting the exact dictionary lookup you need to write. Because the linter packages all of this data into a strict JSON output schema, these prioritized, heavily documented warnings drop seamlessly into continuous integration pipelines. Developers transition from manually hunting for abstract bugs to immediately executing clearly documented, high-impact solutions. The architecture behind the loop anti-pattern linter is highly specialized, merging structural analysis with Big O mathematics. But human developers didn't build it. The agnostic tool was autonomously built from the ground up by Neo, an advanced AI engineering agent capable of writing production-ready code. The loop anti-pattern linter demonstrates that AI is now constructing the surgical diagnostics required to safeguard human logic at scale.